All right, so we're back. Before we get started, I have a small confession to make. At the end of the last video, I showed you a picture and I said, here are some cats. And well, on further review, there was only one cat. And so I wanted to apologize for any confusion that might have caused, although maybe the cat was pregnant. But let's move on. So the purposes of this video is to talk about the variational method. And the variational method is a really important technique in quantum mechanics. It's used all the time in chemistry and condensed matter physics, and in lots of applications where you have a Hamiltonian describing your system and you can't solve it exactly, and it's not even close to something that you can solve exactly, so you can't use perturbation theory, but you still want to get an idea about the physics of the system, and specifically you want to understand what is the ground state energy for the system. And so an example of that, say that you were presented with a hydrogen atom and maybe you're no good at solving differential equations, but you still want to understand how tightly bound is the electron to the proton, how much energy is it going to take to remove the electron from the atom. Okay, but then there's very similar problems where even if you're really good at differential equations, there just is no exact solution. So if you want to understand the binding energies for more complicated atoms or molecules, then you're pretty much out of luck with analytical techniques. And so this is where the variational method comes in. Okay, so our basic idea is that we're given some quantum system, we're given the Hamiltonian H, and we want to estimate what is the ground state energy, E0. Okay, and so the method is based on a simple observation. Okay, so the observation is as follows. So we want to consider just any old state that we pick. So for any state psi, then the quantity psi h psi, so we know what that is. That's going to be the expectation value of the energy for the state psi. Okay, so that is the expectation value Okay, the expectation value of the energy for the state psi. And so what that means is that we can measure the energy in the state psi, we'll get one of the energy eigenvalues, we prepare the state psi again, we measure the energy, we'll get one of the energy eigenvalues, but that energy eigenvalue might be different each time, and each possible value of the energy will come along with some probability. And if we take the average of our results over a lot of measurements, then the average is this expectation value. Okay, so one thing that we can immediately conclude from that, okay, because the average over a large number of measurements where we get the various possible values of energy, well, that average has to be greater than the minimum possible value of energy, which is E0. Okay. So our conclusion would be that E0 is less than or equal to this average. Okay, so that's basically just an obvious statement, but it turns out that it is useful for us. So now consider the following. Let's just turn it around, and let's just imagine picking a state and calculating psi h psi for that state. Okay, so if we calculate psi h psi for any state, then this is going to give us an upper bound for the ground state energy. Okay, so how is that useful? So let's say you were studying the hydrogen atom and you had no idea what the energies were for that atom. But you have the Hamiltonian, you don't know how to solve for the energy eigenstates, but what you can do is just write down some wave function and evaluate the expectation value of the Hamiltonian. I'm going to remind you how that goes in an example in the next video. But let's say we do that. So we just calculate the expectation value of the Hamiltonian in this state. Let's say we get minus 10.6 electron volts. Okay, and so now that's a very valuable piece of information because it tells us that whatever the ground state energy is, it can't be bigger than minus 10.6 electron volts. Okay. Okay, so we probably wouldn't want to stop there. We could just pick another state and then calculate the expectation value of the energy for that one. And if it's lower than minus 10.6 electron volts, then we get more information. And so if we keep picking more and more states, we're going to get a better and better upper bound, or we could get a better and better upper bound for the energy of the ground state. Okay, and so that is basically all there is to the variational method. So our strategy, let me use blue here. So our strategy is, number one, pick a state. Number two, calculate psi for that state given whatever Hamiltonian is specified in the problem. And then we know that this gives an upper bound for E0. Okay, and now we can repeat that. Okay, and so one thing we know is that if we happen to pick the ground state itself, then this is actually going to give the ground state energy. So basically, if we just keep trying and trying and trying, we should, in principle, be able to get our bound to decrease and decrease and decrease and decrease and decrease, and then we'll sort of narrow in on the ground state energy. And if we keep trying and trying and trying all sorts of different wave functions, and we find that our bound is not really decreasing much anymore, then we have a good sense that we might be now close to the ground state energy. Okay, so I'm going to do a detailed example of this in the next video, where you'll see how this actually would be applied.